All right, welcome to lecture. First, a couple of announcements. Your graded midterms 1 are available through Panagrader. You should have received an email about that. If you haven't, let us know. There was a fire alarm in Dwinell during the exam. We also posted about that on Piazza. Read what we posted there. Project 4, Ghostbusters, is out, is due on Friday, 5 p.m. Your homework 7 is also out and is due exceptionally on Tuesday. It'll be on Tuesday after spring break. To avoid I have something due the day right after spring break, we pushed it to Tuesday. But keep in mind, you do have something due on that Tuesday after spring break. Project 3, we've been rounding up the contest results and we'll announce those on Thursday. Any questions about logistics? All right, let's get started on base nets then. In many ways, this is my favorite lecture. And the reason this is my favorite lecture is because the base nets is really what got me personally so excited about artificial intelligence. Like a lot of things we covered are really neat, but for me, this is where I kind of said, well, this really can do something different from what I thought we'd be able to do, and made it really exciting. Let's think back first to the beginning of this class. We were talking about the history of AI. And at some point I said that in the 80s, there was a little bit of a AI winter. It was difficult to make progress. And part of the difficulty was how to deal with uncertainty. And I said then, well, in the 90s, people came up with probabilistic reasoning methods that allowed to deal with uncertainty. And things started to work better that way. And you might ask yourself the question, well, why weren't people using probability distributions before? Certainly probability distributions existed for a long time. People could have used them before. But the challenge really was not just to be aware that probability distributions are a useful thing, but somehow make them computationally practical. If you think of any distribution over, let's say, 1,000 random variables, you want to represent a full joint distribution. Even though you might know that that full joint distribution could do something useful for you, you're just not able to represent it because the table is too large. And so base nets will give us a way to deal with distributions over large sets of random variables in a meaningful way so things become practical. Okay, so what we're going to be doing is to build models. And the main thing to keep in mind, as always, when we build models is that there are always going to be approximations of what's happening in the real world. They may not, for example, account for every variable that's present in the real world. They may not account for every interaction variables might have. But the key thing to keep in mind here is that all models are wrong, but some of them are useful. And so your job as an engineer or designer of these models is to somehow pick a model that's reasonable and is going to be useful. All right, so what do we do with these probabilistic models? In fact, we've seen probabilistic models before. What's a simple probabilistic model? A full joint distribution. What's another way to specify a probabilistic model is to specify, let's say, a marginal over x and a conditional for y given x. Together, that gives us a probabilistic model for the joint over x and y, without explicitly specifying the joint. We've seen another way to specify joint distributions. We could specify a hidden Markov model. It's a very sparse way of specifying a joint distribution over a large set of random variables. It's a little specific. It's for these temporal sequences or spatial sequences, but it does allow us to specify a distribution in a very compact way. Well, what have we done with those models? Often we compute things that are not immediately given. So the simplest scenario here is applying Bayes' rule. You're given a conditional, but it's the wrong conditional for what you want to do, and Bayes' rule allows you to flip that around and get out what you want to get out. In HMMs, we looked at temporal reasoning. As we specify the HMM model, we don't have an explicit model for what is the probability of the state at time t given all evidence up to time t. No, we have a much more fine-grained model just for the local interactions, and somehow from that computed the conditional we care about. All right, things we'll be able to do later are things like diagnostic reasoning over large sets of random variables. Causal reasoning, explore patterns about what is likely to happen given the evidence we have so far. And something else we'll be able to do is computing value of information. This is an intriguing concept. The idea here is that, let's say you have uncertainty about a random variable. How much would you be willing to pay for somebody to tell you the value of that random variable? That's the question we'll be able to answer once we look at value of information. All right. Let's first do a quick recap of a couple of properties that we looked at before, but that are going to be really important in this lecture. The first one is independence. So what's independence? Two variables are independent if and only if the following holds true. This is saying that for all values the random variables x and y can take on, the joint probability of x and y has to be equal to the product of the marginal for x with the marginal for y. All right, so that means they independently contribute to the distribution. There is no interaction here. Right? No way of specifying any interaction between x and y if all you get to specify is the marginals. Another way of writing this is as follows. The conditional of x given y is the same as just the marginal for x. Similarly, you could write for all x comma y, the conditional for y given x is just the marginal for y. These are three equivalent ways of specifying that x and y are independent. You could use either one of those three as your definition, and the other two will be a consequence that you can just derive from that definition. All right, shorthand notation is this notation over here. Let's think about the kind of how realistic is it to make this modeling assumption that variables are actually independent, right? Let's see. In general, it's rare that all variables are independent because usually variables interact in some way. But maybe in some cases there are some subsets of variables that are independent of other subsets of variables. For example, if you consider weather, traffic, cavity, and toothache, you might argue that toothache and cavity together are independent of weather and traffic together. There's no immediate interaction there. Again, this will be a modeling assumption. You never know if that's really true or not, but it might be a really good approximation of what's happening in the real world. All right, so how do we verify independence? If you're given a joint distribution, you can verify independence by building the marginals for each of the variables that are in the joint distribution. In this case, there are two variables, so there are two marginals. And then multiplying those marginals together to construct a new distribution which is equal to the product of the marginals. If P2 is equal to P1, then that means x and y are independent. If any of the entries in P2 are different from the corresponding entry in P1, then they are not independent. So let's see, are they independent? Let's look at the first entry, 0.3 here, 0.4 here. Conclusion, they're not independent because at least one entry differs. All right, where could we actually see independence? Let's say you're interested in modeling coin flips. You have a bunch of coins, maybe 8 if you're an octopus, and you're flipping 8 coins at the same time. And you look at the joint distribution over outcomes of these coin flips. That's a joint distribution over 8 random variables. That joint distribution has 2 to the 8 entries, 1 entry for each possible joint instantiation. But you could argue that the outcome of each of these flips is independent, and maybe you can encode the same information by assuming they're independent and just having 8 tables that look like this that are much smaller, each table only having 2 entries. If there were n coins, this representation here has 2n entries. This representation here has 2 to the n entries, the full joint. So it's a much more compact way of representing, in this case, a full joint by just representing all the marginals and then saying, well, we assume they're independent, so if we want anything from the full joint, all we have to do is multiply together the corresponding entries of the marginals, and that tells us the entry in the full joint. Of course, it's a really limiting assumption to assume full independence. And the reason it's very limiting is because, well, A, it's often not true, and B, if you assume independence, then if you measure a variable, it's not going to tell you anything about the other variables. And that's exactly what we're after. We're after these scenarios where some variables we'll never be able to measure, but others we are able to measure, and we want to infer things about the variables we cannot measure or are not willing to measure, thanks to measuring the variables we can measure. And to be able to make that inference, there has to be a connection between the variables. They cannot be independent, because if they're independent, a measurement of one variable just doesn't say anything about the other one. All right, so there's this notion of conditional independence. Conditional independence is a weaker assumption. For conditional independence, we need at least 3 variables to be able to talk about that. So let's look at this scenario here. Somebody could have a toothache, could have a cavity, and if the dentist robot probes their teeth, that probe could catch somewhere. All right. Then you could say, well, if I have a cavity, the probability that the probe catches in it does not depend on whether I have a toothache. That's an assumption, but it's a reasonable assumption. You could say, well, the mechanics of how this probe catches is based on the shape of the cavity, not on whether the cavity is painful or not. And so just the presence of the cavity or not is what makes it catch or not. Mathematically, this is written as follows. It's saying that the probability of catch given toothache and cavity are true is the same as the probability of catch given just cavity is true. All right, another way of interpreting this is saying that once you know cavity is true, you have a distribution for whether the probe will catch or not. If now somebody told you whether there was a toothache or not, that's not giving you any additional information about whether the probe will catch or not. All right, the same independence holds if you don't have a cavity, so you can write the same thing with negative cavity over here. The catch is conditionally independent of toothache given cavity is what we say if both of those, if these expressions are true for all possible instantiations of these variables. So what this expression is here is an expression that effectively encodes 8 expressions. Each of these variables are binary. Each of them can take on 2 values, 3 variables, so there's 8 possible combinations for this expression. And for each of these 8 possible combinations, that equality holds true. That's what we mean when we write it with the capital letters. We write it's true for the random variable in general. If that's true, then we have conditional independence of toothache, of catch from toothache given cavity. All right, just like we had for independence, different ways of writing the independence, right? We could write it, let's just flip back here. We could write it in 3 different ways, as the joint being a product of the marginals or being allowed to drop what you condition on. So 3 ways of writing this conditional independence. 3 ways of writing this independence. For conditional independence, we'll have the same set of equations, but everywhere we have something extra we condition on at the very end and just carry that through. So here, conditional independence, equivalent statements to the one over here are that the conditional of toothache given catch and cavity, that's switching the role of x and y in what we had on that previous slide. Then in that conditioning, we can still get rid of the conditioning on catch here now. Then this is the joint between x and y equals product of marginal of x with marginal of y. That's written here, but now with additional conditioning on cavity everywhere. And so what's happening here is that thanks to conditioning on a certain variable, other variables become independent conditioned on that variable, and that's a much more reasonable assumption for many real-world scenarios. And that's the assumption we'll be working with throughout this lecture for many examples. All right, so we discussed unconditional absolute independence is very rare, right? And moreover, it's not the interesting case because we can't do much with those distributions. Conditional independence will be our most basic and robust form of knowledge that we'll be encoding into our base nets. So x is conditionally independent of y given z, if and only if this expression holds true for all possible values x, y, and z can take on. Equivalently, you can write it as follows, and then equivalently, you can write it yet in a different way, namely for all x, y, z, the conditional of y given z and x equals the conditional of y just given z. These are 3 equivalent ways of writing the same assumption. How do you prove something like that? Like in this case, that these are equivalent. Okay, let's just work through it. Let's prove that the first one implies the second one, just to give you an example of how this reasoning works. So we want to prove that this equality here holds true if we make this assumption over here. Okay, let's start with the definition of the conditional. conditional of x given z and y is the joint between x, y, and z divided by the joint over just y and z. At this point, we look at our assumption and we somehow want to incorporate that assumption in the calculation because we know that assumption is going to be critical to prove what we want to prove. So this assumption has a conditional of x and y given z. So we want to rewrite things with that conditional. All right, we have the joint between x, y, and z. We can write the joint between those three variables as the marginal for z multiplied with the conditional for x and y given z. Right? That's just the product rule. The joint between a set of variables can be decomposed into the marginal over a subset and then the conditional of the other variables given that first subset. So this is always true. We haven't used the assumption, but we're targeting to now next use that assumption. At the bottom, the joint between y and z. Let's keep that for now. All right, now at the top, we can use our assumption that the joint between x and y given z can be factored as the conditional for x given z and times the conditional for y given z. We're still dividing by the joint over y and z. Now we know we want to simplify things. And we see at the top here, we have the conditional of y given z, and this is the marginal for z. We know that the joint between y and z is the same as pz times py given z. That's again just a product rule. We chose to apply that product rule because we saw it would match things up with what we see on the top. And now we can simplify. This cancels out, and we're left with the conditional for x given just z, which is what we had to prove in this particular case here. All right, and you can try this for yourself. You can see if you can go from the first one to imply the last one, and in any combination, you should be able to prove that you can start from any of these three definitions and prove that the other two are equivalent. All right, we now know what the formal definition is of conditional probability. We reviewed it. We saw there's three ways of defining it. That also means three ways of using it. Let's look at some examples. Oh, before that, let me just re-emphasize the notation here. This is the notation we'll be using for x independent of y given z. All right, so a first example. We looked at this before, but it's so important in this lecture that I want to review it. Let's look at the domain where we consider traffic, umbrella, and raining. What's a reasonable conditional independence assumption to make here? Thinking about how they interact and what might be independent of what given the third one. Any thoughts? Patrick? So the suggestion here was that if we condition on raining, then the other two variables are independent of each other. Traffic independent of umbrella, which by the way equivalently can be written this way. The order here doesn't matter. Why is this reasonable? Well, you can imagine that the way the world works is that there could be rain or there could not be rain. And then whether there is rain or not determines whether somebody will carry an umbrella or not. And independently, whether there's rain or not will determine whether there's a lot of traffic or not. But there is no interaction there where people carrying umbrellas causes more traffic or the other way around. If you thought there was such interaction, if you thought that everybody driving their cars starts rubbernecking and looking at people with umbrellas because that's so cool to look at, then you would not have this independence, right? So it's always an assumption. You need to be aware of the assumptions you're making. In this case, we just explained the assumption we're making. If you're happy with it, work with it. If you're not happy with it, well, then use a different model. All right, another example. Fire, smoke, and alarm. Any conditional independencies that seem reasonable here? Yes? Okay, so the suggestion was that given smoke, fire and alarm are conditionally independent when you conditional smoke. Why might that be reasonable? Well, especially if you look at this cartoon drawing here, what this is suggesting is that there's a smoke alarm. It just triggers on smoke. That's the assumption. It just Doesn't trigger based on whether it's hot or not. It just triggers based on whether there is smoke coming into the alarm. So once you know there is smoke, saying whether there is a fire or not is not telling you anything about whether the alarm will go off or not. Similarly, the other way around. Once you know there is smoke, if somebody in addition tells you the alarm is going off, doesn't tell you anything about whether there's a fire or not, because you already knew there is smoke. That gives you all the information that you can get in this scenario about whether there's a fire or not, short of actually measuring whether there's a fire or not. So this is a reasonable assumption here. Of course, you can always have worlds where things work differently. All right, so we've seen a couple of examples. Now, let's look at how conditional independence is going to be key in everything we're going to be doing. And the way it's going to be key is through the chain rule. So remember the chain rule. The chain rule said this is true always. For any joint distribution, you can write the full joint as a product of conditionals. And the way you do it is you pick an ordering of your variables, and then you follow that ordering. You start with the first one. You have the marginal of that first one, then the conditional of the second one given the first one, conditional of the third one given the first two, and so forth. You can do this in n factorial different ways, right? You have n factorial choices to order your variables. You have n factorial different ways to apply the chain rule to a joint distribution over n variables. All right, now let's take a look at how the combination of chain rule and conditional independence is going to give us leverage. All right, let's look at the joint distribution for traffic, rain, and umbrella. Okay, applying the chain rule gives us this equation over here. This is always true. We have made no assumptions. Now, if we're willing to make an assumption, the assumption we talked about, namely that umbrella and traffic are independent given rain, that means that we can get rid of this in the back of the conditioning here. All right, so with the assumption of conditional independence of umbrella and rain given, umbrella and traffic given rain, we get this new expression here. Why is this really interesting? The size of the distributions is different. Over here, you have a conditional for one variable given two variables. At the bottom, you have a conditional for one variable given one variable. In general, if you have a conditional distribution, and let's say you condition on k variables, so you have a conditional of some variable y given x1 through xk, what's the size of the distribution that you are encoding here? Well, for all possible combinations of what appears in the back, let's say binary variables, 2 to the k combinations, you have to specify probability that y is true versus false. So effectively, you have 2 to the k entries, or maybe 2 to the k times 2, depending on how you do it. So if you can reduce the number of variables behind the conditioning bar, that is a really good thing to do, because the number of variables there appears in the exponent, and we know things that appear in the exponent tend to be bad, because they tend to blow things up. Right? So getting rid of things behind the conditioning bar is great, and we see that conditional independence exactly does that for us. If you're willing to assume conditional independence, in this chain rule expression, you will be able to get rid of things behind the conditioning bar. Of course, then also you need to think about in which order you apply the chain rule, right? So one thing you'll have to be careful about is there's so many ways to apply the chain rule. You're going to want to apply it in an ordering such that your conditional independencies match up with the expressions you have, and indeed you can get rid of things behind the conditioning bar. Often, the way to get this done is to think of things as a causal process. If you think of variables somehow being sequenced in some way, that doesn't have to be true, but if you think of it in that way, then often the ordering you pick according to that causal process will give you the ability to cross things out behind the conditioning bar that are corresponding to reasonable conditional independence assumptions. All right, so that's going to be the main trick we're going to be playing, but we're going to be playing it in a somewhat cleaner way than I've said so far. We're going to introduce this notion of base nets, which will allow us to do this a little more conveniently than just kind of throwing chain rule expansions at things and then assuming conditional dependencies and have it work out in this kind of very algebraic way. We'll do something that's more graphical, use graphical notation, have graphs representing our distributions. It'll work out more easily for us. But the key idea is just this. That's the idea base nets will exploit, is that you apply the chain rule, you apply a conditional independence assumption, and it simplifies these conditional distributions, makes them smaller. Smaller is good. easier to store, easier to specify, easier to work with. All right, let's look at a small example. Here's Ghostbusters again. And a natural way to think about what's going on in Ghostbusters is that you have a sensory model, right, that tells you something about what happens when you measure, right? In this case, there are just two locations for the ghost, top or bottom, right? You could have a measurement on each of these squares, so each of them could give you a red measurement or not a red measurement, so those are two random variables. And then the ghost being in the top is the other random variable, the third random variable. If it's not at the top, it's at the bottom. So to specify the interaction between these three random variables, in general, you'd need to specify a full joint distribution, right, in some way. And we're going to do this now in a very compact way. So we say, well, let's just specify these local interactions. We have a prior over where the ghost might be. We assume that these sensor readings are independent. Given where the ghost is, the sensor reading that we get at the top is independent of the sensor reading that we get at the bottom, because the sensors are not related. That's the assumption. There's nothing that relates them except for that they're measuring where the ghost is. That's how they relate to each other, but not in any other way. So effectively, we specified three distributions here: for the ghost, for top sensor given ghost, and for bottom sensor given ghost. In general, that's not enough to specify a full joint distribution, but if we're willing to assume the two sensors are independent, given where the ghost is, then this is enough. So we have the joint for ghost, bottom sensor, top sensor. We apply the chain rule, which tells us that's equal to distribution for ghost times conditional for top given ghost, conditional for bottom given ghost and top. The conditional independence assumption that we're making is that the two sensors are independent, given you know where the ghost is, which means we can get rid of this one over here. And what we have now here is exactly these distributions specified over here, and we can multiply them together the right way. We get a full joint distribution. I'm not saying we should multiply them together to get the full joint distribution, but we could. In practice, often the full joint distribution will be too large, will not fit on a slide for sure, and you wouldn't actually want to multiply everything together to get the full joint, but you know that the chain rule tells you, if you're interested in any entry in the full joint distribution, the chain rule tells you how to compute that entry that you care about, or multiple entries you might care about. Okay, so now we're ready for actually really starting to look at Bayes nets. It's a new way of representing joint distributions. It's very closely related to the chain rule. I've already hinted at that. It's not just a new way of representing full joint distributions. Once we've seen Bayes nets, you realize you start thinking about probability distributions in a different way. And that's really key here. That you go from thinking of probability distributions as being these big tables where you have an entry for every possible joint instantiation of the variables, to this new representation, this Bayes net representation, which A, will be more compact, and B, will expose a lot of the structure in the distribution, right? If you're going to look at a Bayes net, you'll be able to just read off certain assumptions that were being made that are very difficult to read off from looking at just a full joint table. So overall, what's going to be really important is that we're going to have a new way of thinking. It's going to be a more graphical way of thinking. We're going to be looking at graphs, and those graphs are going to be representing probability distributions. And by looking at those graphs, we'll be able to say things about those distributions without ever looking at the numbers in the full joint table. Question there? Okay, that's a great question. So we've always talked about discrete random variables, and then a distribution can be a table. If you have continuous random variables, then the way to represent the distribution is commonly done using a probability density function, which effectively encodes how much probability mass is associated with each interval if it's a one-dimensional distribution, or each volume in space. What's the probability of landing in a certain volume of space? It turns out if you had continuous random variables, you can still use Bayes nets. And the conditional distributions that you'd be working with would then be conditional distributions that are densities rather than the kind of discrete distributions that we're working with. But the same intuitions will be true. We're not going to bother with those in 188 because the intuitions are really the same, discrete or continuous, but the math is a little simpler in the discrete way. We don't have to compute integrals, so we stick with the discrete setting. But definitely you can generalize all of this to continuous variables. All right, so let's start looking at Bayes nets. So why do we care? There are two problems with using full joint distributions as tables as our representation of probability distributions over large sets of random variables. First of all, only when there are very few variables is it practical to kind of write down that distribution. We can't store it if there's many variables. It'd be way too large. The other thing is that it's really difficult to either specify the entries in a full joint table or to learn them from data. We don't know yet how we'd learn them from data, but we'll see later. It's difficult to learn from data if you need to learn many, many entries. It's easier to learn a small set of parameters. The other thing is if you're going to specify something by hand, if I tell you specify to me the full joint distribution over 100 random variables by hand, that's really difficult to think about. It's easier to think about how variables that are closely related to each other in some way interact and specify local interactions. And that's what we're going to be after. So Bayes nets will be a technique for describing complex joint distributions, so models, using simple local distributions. Often they're called graphical models because, I mean, technically it's not that we're just applying Bayes rule in a Bayes net. It's, a simple Bayes net, Bayes rule might be applied effectively when you do it, but once you have more than two variables, it gets more complicated. But just, I guess that's the name that people use. Bayes nets, another one people use is graphical models. We'll describe how variables interact locally and somehow be able to infer from that their global interaction, which will still exist, but we won't have to specify it. For the next 10 minutes, I'm going to be very vague. So I'm not going to be very precise about mathematically what's going on. We're just going to build some intuition about what we want to do, and then we'll formalize it after we've done that. So here's the first example. Let's say you want to specify a distribution that models this insurance domain. There are 27 variables here. 27 variables, let's assume they're binary. So 27 variables, let's assume they're binary. That would mean 2 to the 27 entries, which is equal to about 134 million entries. So if you wanted to model this domain the naive way, you'd be busy specifying a table with 134 million entries, which is just impractical. I mean, A, nobody's probably willing to spend the time, and B, how would you even know what these numbers should be? If somebody tells you in the full joint distribution, what's the probability of plus age, negative socioeconomic, plus good student, minus extra car, plus mileage, and so forth, that's a really difficult probability to come up with and say something meaningful for. So instead, we're going to look at these models here, as shown in this graph, where we just model local interactions. So for example, what we have here is socioeconomic status. And we're saying that there's an arrow from that to extra car, actually the same kind of arrows we've seen in HMMs. And that's saying that we will be specifying a conditional distribution for whether there's an extra car in that household, whether or not there is one, depending on the socioeconomic status. That's something that's reasonable. That's just an interaction between two variables. That's something you can come up with with numbers for. Here, good student is assumed to depend on socioeconomic status and age, maybe, at least in this model. We can look at any of these variables and we can see which other variables can directly influence them. Anti-theft. Will there be an anti-theft device in this car? Well, it seems like it's dependent on socioeconomic status and dependent on risk aversion of that person. So overall, there's a lot of variables here. And then point one is, let's say, accident, whether that's likely to happen or not. As an insurance company, you want to kind of somehow build these interaction models, and then based on the data you are able to observe about a person, compute the probability of accident, maybe compute the probability of that this accident causes a lot of damage, and so forth, and then based on that, compute your expected risk that you're taking insuring this particular person, right? And that can then tell you something about how high the premium is that you want to charge for that person. All right, so here you could model this domain with 27 variables through just local interactions. But that doesn't mean we don't have the global interaction encoded implicitly. We can still make global inference because overall they all interact. Here's another example. Let's say you are troubleshooting something, in this case your car, and you build a model for how the troubleshooting process might proceed, right? There are causes, things that could go wrong, and then they might cause other things to go wrong, or they might cause certain measurements that are a noisy observation of what went wrong. So in this case here, it could be that the alternator is broken, it could be that the fan belt is broken. That in turn could lead to the battery not charging, which in turn could lead to the battery being flat. At the same time, if you look here, the battery being dead could also lead to the battery being flat. And so battery flat is somehow dependent on those two variables in some probabilistic way. Now we have more diagnostics at the bottom here, right? Often the things at the bottom are the things we're able to measure. Those are the effects, the sensory measurements, just like we had in an HMM. But it doesn't have to be that way, right? You could measure any of these variables in principle if you had the right tool to go and measure them. Key here is that in this case, we have 16 variables, and 2 to the 16 is 65,000 approximately. If you needed to specify 65,000 entries in a full joint distribution, it'd be taking you a long time and be very difficult to be precise about what these probabilities should be for these full joint instantiations. The models we'll be working with don't bother doing that. They just say, all we're going to do is model how things interact and then specify the local interactions. What's the worst kind of local interaction you have to specify here? Where do you have the most work? Car 1 start is what I'm hearing. Why is that true? Well, we know that the size of a conditional distribution is effectively 2 to the k if it's over binary variables that you're conditioning on, where k is the number of variables you condition on. So the number of variables you condition on will determine how big the table is that you specify. Well, car 1 start has the most parent variables, and so its conditional distribution will be the largest one in this particular Bayes net over here. All right, so what is this notation we've been looking at, right? I've given you examples. We have some intuition of what's going on, but I haven't told you what we're actually showing here. Nodes in these graphs are random variables, right? For example, this is a node in a graph with only one node, and that's our random variable in this graph, our one random variable. They can be assigned or unassigned, depends on the situation. Often the ones that are assigned, we shade in with gray, and the ones that are unassigned, we leave just with a white background. All right, the arcs indicate interaction, direct interaction. There's indirect interaction between all variables, typically, when you can find a path connecting them. But the direct interactions are indicated by the arcs, not mitigated through other variables. Formally, what they really mean is that if an arc is missing, effectively you're making a conditional independence assumption. You're saying, to specify the distribution of this variable, it's enough for me to condition on its parents. I don't need to condition on all these other variables. That's the formal assumption. But intuitively, you're encoding the direct interaction between variables by adding arcs. Okay, so here's our toothache cavity catch example. There could be a cavity or not, and then that could cause a toothache or not, could cause a catch or not, and this would be our corresponding Bayes net. All right, so for now, let's assume all of these arrows mean direct causation. It's often true, but it doesn't have to be true. Mathematically, we'll see it doesn't have to be true. In practice, very often it is true, because those are the kind of models that are easy to work with and are convenient. Okay, so let's take a look at a very simple Bayes net. What happens if we have n independent coin flips? What does the Bayes net look like? Suggestion over here. The suggestion is a Bayes net without any edges, because there are no direct interactions, no interactions at all. So this would be what our Bayes net looks like. This is absolute independence. We know that's not all that exciting, but it's an example of a Bayes net. How about traffic domain? Right. The variables here are rain and traffic. What's a reasonable Bayes net here? So let's pick somebody from the back. Anybody in the back who has a suggestion? What kind of Bayes net might make sense here? Over there, Colin. Rain to traffic. Why? Because rain is in some sense the cost that might then cause traffic to be busier or not. All right. So that's a reasonable Bayes net to pick, but you could pick any of these two Bayes nets. Here are two Bayes nets. Both of them are Bayes nets. Both of them have two random variables, rain and traffic. Both of them will specify a full joint distribution once you specify a distribution for rain in both cases, and then one for just traffic here, and one for traffic given rain for the second one. But the suggestions were all to pick the second one. Why would we prefer the second one? Well, if you're stuck with the first one, if somebody tells you something about traffic, the computation you can do with the first one will not tell you anything then about rain because they're considered independent. You're not able to reason about one variable given the other variable. And we know there's interactions, so the first one is not a great fit for most things you'd like to do. Second one here will be the better fit. All right, let's look at a bigger traffic example. Okay, here is a new scenario. There is a dragon who could have a toothache. There is traffic. There is a ballpark. There could be rain or not. And there's a home that has a roof that could be dripping or not. All right, let's build them up one at a time here. So first thing, traffic. That's the only variable we have so far. Okay, well, let's just put it somewhere. Let's put it in the middle here so we have enough room for the other variables to come on top or below, depending on how we think they should show up. Next one, rain. We thought about that already. We think rain is the one that could cause traffic, so we'll put it on top here, arrow from rain to traffic. How about low pressure? I'm hearing low pressure to rain. Why is that meaningful? Well, we think the amount of pressure will have an effect on whether it rains or not, and so that's a reasonable model. How about an arrow from low pressure to traffic? Does low pressure affect traffic? It actually does affect traffic, but it's mitigated through the rain in the model we're using. And so since it's mitigated through the rain, we don't put a direct arrow from low pressure to traffic. We just let it be the way it is right now on the slide. D, roof drips. Rain is what I'm hearing, which makes a lot of sense, right? Whether the roof drips or not is influenced by the rain and not by these other random variables. Then, whether there's a ball game or not. So I hear rain and traffic being connected to ball game as the random variables that directly interact with ball game. So let's put it somewhere here. Now we need to choose the direction of these arrows. Ball game definitely could be assumed to cause traffic, because if there's a ball game, there's a lot of traffic probably. If there's no ball game, there's less traffic. Then a ball game could be canceled when there is a lot of rain. So we could have an arrow from rain to ball game here. All right, cavity. Some people say low pressure. Maybe the very high pressure can dig into your teeth or something and cause cavities. That's reasonable if you think that's the way it works. A lot of people might argue that it would be sitting here and wouldn't all that directly be related to any of the variables. All right, so that's one example of how things could play out. Keep in mind that all these things are up for debate, right? Assumptions, you need to understand what assumptions you're making. There's not just one right model. You just need to understand what assumption you make when you pick a particular model. The other thing to keep in mind is these variables, for example, let's say whether your roof is dripping or not, can tell you something about whether there's traffic or not. Because you see a roof dripping, which tells you something about whether it's raining or not, which in turn tells you something about whether there's traffic or not. But there's no direct arrow, because the effect is mitigated in the model we have through whether it's raining or not. All right, let's look at what is one of the most frequently chosen examples for Bayes nets. If you look in the book, you'll see this example. Look pretty much anything about Bayes nets, you'll see this example. What's the story here? There is John, there is Mary, there could be a burglary happening, and there is an alarm that could go off. And then there is an earthquake that could be doing things to you or to your house and so forth. All right, so let's build it up. The variables are, first one, burglary. So let's put it down in our Bayes net. It's the only one, so nothing to worry about yet. Next, oh, not a good space. Let's put it here. Whether the alarm goes off or not, is that influenced based on whether there's a burglary or not? Yeah, if it's a burglary alarm, one that reacts on those kind of events, definitely, right? So you want an arrow from burglary to alarm. Next variable, your neighbor Mary calls you or not. So here it really depends on the kind of assumptions you're making. The assumptions made in the typical story here is that your neighbor Mary doesn't really look at your house, but if your alarm goes off, she'll hear it. That's the only way she interacts with your house. So she wouldn't see the burglar, she wouldn't see anything about your house, but she'd hear the noise if your alarm goes off, and then she might decide to call you. She might go, I should give my neighbor a call because this alarm is kind of annoying me, or maybe because they should be aware their alarm is going off. So we have a consequence here. Mary might call as a consequence of whether the alarm is going off or not. Next one, your other neighbor, John. He might call you or not, depending on whether he hears the alarm go off. So similar to Mary, John, it's just one parent in this network here, whether the alarm is going off or not. Okay, you could argue with this, right? You could say, well, my neighbor John, he always is looking out of his window and looking at my house, and he would know if a burglar comes in, so I should also put an arrow here from burglar to John. But that's not what this story assumes. This story here assumes your neighbors are just listening to things, not watching things. All right, then earthquake. Well, an earthquake could shake your house around. That could affect your alarm, and so your earthquake event could cause your alarm to go off. That's the model a lot of people use. Understand the assumptions. Understand that you could want to use a very different model, right? You could say, well, I think earthquake causes burglaries because all the chaos of the earthquake will cause burglars to come out and do a lot of damage in addition to the earthquake. Probably true, but this model doesn't assume that. All right, so let's formally look at the semantics now. Actually, let's take a short break and then let's formally look at the semantics of Bayes nets. Then let's formally define what a Bayes net is. What makes for a Bayes net? A Bayes net has a set of nodes, one per variable x, let's say. These nodes are connected in a directed acyclic graph. This is a constraint. Not every graph is an acyclic graph. What does it mean to be a directed acyclic graph? It means that if you are to follow the direction of the arcs in your graph, you're never able to complete a cycle. That's what it means to be directed acyclic. So let's give an example here. This is a directed acyclic graph. This is also a directed acyclic graph, because if you follow the direction of the arrows, you're not able to complete a cycle. If I were to flip the direction here and make this one point that way, now it's not anymore a directed acyclic graph, because now you can follow the direction of the arcs and complete a cycle. So this is no good. But cycles are okay as long as you cannot follow them, go around the cycle as you follow the direction of the edges. All right, so directed acyclic graph, the nodes correspond to the random variables, and then each node has a conditional distribution associated with it. So let's look at one node here, the node x. X is a set of parents, a1 through an, and the conditional distribution that you put with that node x is a conditional of x given its parents. Right, this matches well with what we've been talking about just intuitively, saying that we're modeling direct interaction with these arcs, and that is what we're doing here. We're saying what we specify for a variable is a conditional for that variable given its parents. All right, so the Bayes net consists of both a graph and the local conditional probabilities. Often they're a description. These arcs are a description of a noisy causal process. In the examples we've looked at, that's been true, but it doesn't have to be true. But often that's how it plays out. This is not part of the definition. This is just an aside. Like, this is often true, but the definition is that you need a directed acyclic graph and conditional distributions for each variable given its parents. All right, so how do we associate probabilities with this Bayes net? Okay, the way we compute a probability from a Bayes net is by multiplying all these conditional probabilities together. So I'm going to make a claim here. For now, this is a claim. I haven't shown this. I'm going to claim that if you're given a Bayes net, which is a directed acyclic graph and a conditional for each variable given its parents, you can recover a full joint distribution over that set of variables by multiplying together all these conditional distributions. That's what this equation is saying. The full joint is the product of the conditionals that you have in your BaseNet. All right, so let's look at an example. Let's say we have our simple BaseNet here, cavity, toothache, and catch. We're interested in the probability in the full joint distribution of plus cavity, plus catch, negative toothache. All right, the way we compute that from the BaseNet is we look at each variable. First one is cavity. That one has a distribution just over cavity because no parents. So from that table for cavity, you just read off the probability for plus cavity. Then the next variable, catch. Okay, you look at that variable's table. That's a conditional for catch given cavity. From that conditional distribution, you read off plus catch given plus cavity. Then we go on to the third one, which is toothache. It has a conditional distribution for toothache given cavity. We look up in that conditional distribution the probability for negative toothache given positive cavity. We multiply all three of these quantities together. I'm going to claim that is a proper way of computing the probability of the joint instantiation of these three variables taking on these three values. So effectively what's happening is, as you're giving your BaseNet and you ask for a full joint instantiation, you just look into every table, and in that table you look at the entry that's consistent with that full joint instantiation and pull it out of that table and then multiply them all together. So far this is a claim. Haven't shown this. Now we're going to show this. All right. Why is it the case that if you specify a directed acyclic graph and then you specify a conditional distribution for every node given its parents, if you multiply those conditionals together, you get out a full joint distribution? Well, one thing we know is going to be true. If we multiply conditional distributions together, all entries will be positive. So all entries that we compute this way will be positive. The one thing we do have to worry about is, do they sum to 1? Because if they don't sum to 1, then we actually didn't construct a joint distribution. We constructed something else. So how do we know this is going to sum to 1? How do we know this is a full joint distribution? All right, so let's go back to the chain rule. The chain rule tells us that the full joint over n variables can be written as this product over here. Right? This can be done in n factorial different ways. This is one of them. We numbered the variables in the way that's consistent with the way we apply the chain rule here. Okay, so this is valid for all distributions. Now, let's assume conditional independences. And this is effectively the assumption you make when you build a BaseNet. This is the only assumption we're making. We're not making any assumptions about causality. We're not making any assumptions about anything but this thing over here. This is the one assumption we need to make. For every variable xi, assume that the conditional of xi, given all variables that preceded in the ordering we're working with, is the same as the conditional of xi given just its parents. Right? Parents, that refers to the BaseNet, right? You look at the BaseNet graph and you're saying, well, of all the variables that precede xi, which are the parents of xi, and only conditional on those is enough. So it's a conditional independence assumption. This is saying xi is independent of x1 through xi minus 1 minus its parents, given its parents. That's the assumption we're making. And for each of these variables, that's the assumption we're making. It's an interesting assumption, right? Remember when we're thinking about how big are these conditional distributions? The assumption we're making here is one that we're independent of some variables, means we can scratch things out behind the conditioning bar, make the table smaller, and we can read off here what they are when we draw a BaseNet. It's exactly this assumption. Okay, if we make that assumption, then this expression over here becomes this expression over here. And that's how we define the joint distribution for BaseNets. Now, a little caveat here. The derivation I made only works out, of course, if the ordering of the variables I wrote out here is consistent with the ordering of the variables in the BaseNet. So you need to pick an ordering of variables, x1 through xn, that's consistent with a a linearization of your BaseNet graph. There are often many linearizations. Any of them will work. You pick a linearization, apply the chain rule for that linearization, then apply these conditional independence assumptions, and you get out this here, which is how we defined the joint distribution for a BaseNet. All right, any questions about this? Yes?
Another way of saying that stuff we made the effect like that, for instance, nothing affects all the ones that
That is one way to think of it, but I think it's better not to think of it that way, because in BaseNets, even though HMMs are a special BaseNet and time is present in HMMs, it's not the case that all BaseNets have time, some kind of notion of time. It's also not true that they need to encode causal assumptions. So I do want to be explicit about that. That is something different. What is true, of course, if you have this causal structure to your BaseNet, which is the typical scenario that you're describing, then it will be true that you'll be able to drop a lot of these variables here, right? So the scenario you're describing is a scenario that's common, but it's not required to have a BaseNet. It's common because it's the one where it's really useful to have a BaseNet. If things only influence a couple of things behind them, so to say, or below them, then the parent set will be very small and you have a very compact representation. A consequence here is also that not every joint distribution can be represented by a given BaseNet. If I give you a BaseNet, let's say I tell you, oh, here's my BaseNet, x1, x2, and then x3. There are many joint distributions that I can encode by this graph, but not all of them, because there's a limitation here. By specifying this graph, I am assuming that in this case, actually, let's pick a different one that we've already covered. So it's a bit more of a review. Let's look at this BaseNet here. We assume that x3 is independent of x2 given x1 here. That's an assumption that we make when we draw this BaseNet, which also means that any distribution that doesn't satisfy this assumption, we cannot encode with this BaseNet. No matter what our choices of conditional probability distributions, this will always be true. It's an assumption we're making. And so most distributions, if you generically write down a distribution, will not satisfy that assumption, cannot be encoded with this particular BaseNet graph. There are BaseNet graphs that don't make any assumptions, right? What's the BaseNet graph that doesn't make any assumptions? It's when you don't get rid of anything here, right? When you look at this conditional independence, you say, is it conditional independent of nothing really given its parents? You need to put everything in its parent set, right? So that would be, in this case, if you add an arrow this way. Now, you can all of a sudden represent every distribution because you made no assumptions. x1 was the first variable, nothing had to happen there. x2 given x1, nothing was assumed away. x3 given x1 and x2, that's just like the chain rule if you expand this. So you can always draw BaseNets where the parents are all the preceding variables. The parents of xi are x1 through xi minus 1. You lose no expressiveness at all. You also don't gain anything. Because if you now look at the size of these conditional distributions, they'll be huge. Just as big, the last one will be just as big as the full joint distribution. So you are making these assumptions, limiting the size of the parent set to have more compact representations. But there are equally valid, mathematically at least, BaseNets that don't make any assumptions and effectively are equivalent to the chain rule. All right, now we formally know what BaseNets are. Let's look again at a couple of examples. Here's our simplest BaseNet, n independent coin flips, no connections. How do we compute the joint probability of this? Let's say we're 4 variables of head, head, tail, head. Well, we look up in the corresponding tables. We look up over here, head, 0.5. Then the next one, also head, so we grab that, 0.5. Then somewhere here there will be x3, from which we grab tail, which will also be 0.5, and then x4, let's say n is 4, will be heads, and we grab it from here, 0.5. Multiply them all together, and we get 1 over 2 to the 4th. That's the probability of this joint instantiation. All right, simple one. Here's another one. Traffic example. Rain or not might cause traffic or not. The BaseNet looks like this. There's a graph, and then there are tables. One table for each variable, conditional of that variable given its parents. What's the probability of plus r negative t? Well, we know we can just apply the definition. It's probability of plus r times probability of negative t given plus r. Then we just look up the numbers. Plus r over here, negative t given plus r over here. So it's equal to 1/4 times also 1/4. 1/16. So that's the semantics of a Bayes net. Let's look at our alarm example. Okay? This is the graph of the Bayes net. We now know things, right? From our definition of Bayes nets, we know what we have assumed here. We know we effectively have assumed, right? We think of any linearization of this graph, and we can think of it as let's say we think of it as B, E, A, J, M as our linearization. We didn't assume anything about B, right? The chain rule would have given us just B already. For E, we assumed E independent of B, because we didn't grab B as a parent. And for A, we made no independence assumption. We grabbed both preceding variables as the parent. No assumption made for A. Then for J, we made the assumption that J is independent of burglary and earthquake given alarm. And then for Mary, we make the assumption that Mary is independent of burglary, earthquake, and John given alarm. Those are the assumptions we made. If you look at the chain rule for that linearization and the things we left out to get our Bayes net distribution, those were the assumptions. The full Bayes net, of course, also has all the tables. So this is the full Bayes net, including the tables. Should it be a surprise that the alarm table is the largest one? No, right? We know that whichever variable has the most parents is going to have the largest table, size 2 times 2 to the k, where k is the number of parents. Right? And then if you want to compute any entry in the joint distribution, you just multiply the corresponding entries together. Let's say you're interested in the probability of plus b, negative e, plus a, plus j, plus m. You just look at the corresponding entries in these tables. First table, plus b is sitting over here. Next table, minus e sitting over here. Then plus alarm, but the alarm has other variables showing up in its table, burglary and earthquake, so it's plus b minus e plus a, plus b minus e plus a, thank you, over here. Then John calls plus j, but it also has the alarm variable, which is in this case plus a, so plus j plus a. And then we have Mary calls this entry over here. Multiply those 5 entries together, we get the joint probability of that particular instantiation. All right, now that we've looked at Bayes nets and we've kind of built the intuition of what we're doing, right? Typically when we draw them out, we have this causal pattern. I'm going to shake things up a little bit and show you something that kind of should remind you of the fact that the causality is not a mathematical assumption, right? Causality was just something we did when we draw the Bayes net because it's convenient. But go back to this thing over here, right? What we showed here, nowhere on this slide was there anything saying this causal assumption is assumed to be true. It's not happening, right? Happening nowhere on the slide. All we needed was this assumption over here. So you can use Bayes nets without any causality assumptions. You just need to be able to make assumptions of that type. Now, it is true that usually when there's causality in your graph structure and so forth, you'll be able to make a lot of assumptions of that type that are very meaningful assumptions. In that sense, causality does play a role, but mathematically, it doesn't play a role. So let's take a look at how this shakes out for our traffic, rain traffic example. So what we have here is a Bayes net. Rain could cause traffic is the way we think about it. We have a full Bayes net, graph, and tables. We can compute the full joint shown over here. All right, with that full joint, we can do whatever we want. Look at those entries. 3 over 16, 1 over 16, 6 over 16, 6 over 16. 3, 1, 6, 6. All right, 3, 1, 6, 6. Now we have a new Bayes net. We reverse the direction. We have an arrow from traffic to rain. Still a Bayes net, right? All we need to do is now specify a marginal distribution for traffic and a conditional for rain given traffic. There are different distributions from the previous slide that we need to specify, but they're still distributions. It's still a reasonable thing to do mathematically. We multiply those together, to get our full joint distribution? 3, 1, 6, 6. Same numbers. So what we see here is that there are two Bayes nets. They look very different. They're specified by a different graph. They're specified by a different set of tables. But the joint distribution they encode is actually the same joint distribution. This one is not causal at all, the way we think of this. Well, what's causal about that? We know that if we think about causation here, it's going to be the other way around. Yet, with this Bayes net, we can still encode the same distribution as the one we had before. Okay, so that begs the question, how does causality come into play, right? Why do we care about causality? When do we care, and so forth? First thing we at least know now is that Bayes nets don't need to be causal. Because at the end of the day, all they encodes a probability distribution. And we showed one there that was exactly the opposite direction, and it still encoded the right distribution. So they don't have to be causal. Often, we choose them to be causal. And the reason we choose them to be causal is that often you'll end up with fewer parents. Why is that? Think back to that definition where you look at the conditional of your variable given all preceding variables. If there's a causal process there, then a lot of things will mitigate it to just a few variables, and things will work out for you, so you condition on very few preceding variables. So you'll be able to make reasonable conditional independence assumptions that match up with your Bayes net structure. Another reason that causal is often preferred is that it's often easier to think about. You look at your Bayes net, you understand what's happening, you understand the patterns that are being exposed, the patterns that you're trying to infer, and so forth. Also, often it's easier to infer these things from experts. It might be easier to go talk to an expert and say, hey, what is the probability of high traffic given there is rain? What's the probability of high traffic when there is no rain? That might be easier to ask an expert because they might have a model of, well, this is how rain affects traffic, so I can tell you the conditional distribution, at least a reasonable one. The other way around is much harder. If you go to an expert and say, what's the probability of it raining when I say there is high traffic or low traffic? Now it's tricky because that doesn't really just depend on traffic. That's not how the process works. So causality comes into play in subtle ways here that A, your network will often be sparser. If you pick an ordering, that's a causal ordering. B, it's easier to specify all the entries in your tables. And lastly, it's easier to understand what's encoded in your network. But they don't need to be causal, as we saw. And let me give another example of something that's not causal. Let's say we look again at rain, traffic, and roof dripping or not. This is a reasonable causal network. We know we like that because it's easy to specify conditionals and so forth. But what now if somebody says, you know what? I just care about traffic and the roof dripping. I don't want to deal with this whole rain thing. I want a Bayes net just over traffic and over whether the roof is dripping or not. What's that Bayes net going to look like? Well, you know they're not independent, so you don't want to just have two separate nodes, because you know that there's this rain thing that relates them. You're not going to put rain in your model, so you're not going to be able to mitigate the effect through rain. In your new model, we only have two variables, but you still want them to not be independent. So, I mean, what are your choices if they're not independent? You have two choices. One is to get the arrow to go traffic to dripping. The other one is for the arrow to go the other way around. Which of these two do you prefer? Well, it's hard to have a preference here, right? In some sense, they're the same. Either one of them is just not really encoding the causal process. And it's probably not the greatest model. Probably the model with 3 variables is the one you should have gone with because you'll be able to reason more accurately about things that are happening. But if somebody forced you to go with a model with 2 variables, this would be a reasonable choice. The other way around would be a reasonable choice too. And if you put in the right numbers in those conditional probability tables, you'll end up with the same joint distribution. They'll be the same model, just with a different graph and different way of specifying the same model. Okay, so we know topology may encode causal structure. It doesn't have to. Keep in mind, what it always has to encode is this assumption over here. There's no way around that. That's part of the definition of Bayes nets. One thing I want you to think about here is what happens if your graph does have a directed cycle, right? What happens if your graph has a directed cycle, which we don't allow for Bayes nets, and we just multiply the conditionals together? Are we still getting a joint distribution? And the answer is that no, you're not guaranteed to get a joint distribution. And the reason is we can't, and the way that we can see this is we cannot apply the chain rule the same way we did, right? Once you have a cycle, there's no way of having an ordering of variables that's consistent with your Bayes net, because there is a cycle, so things are never really behind each other in a specific way. But as long as you have a directed acyclic graph, you can have a Bayes net, and this is the assumption you're making. All right, so where are we at with Bayes nets? So what we've seen so far is what a Bayes net is. We've seen that it's a way to represent a distribution over lots of random variables in a very compact way by encoding local interactions. It's a much more reasonable thing to do. Next, what we're going to look at in Thursday's lecture is, now we know that a Bayes net consists of a graph and then conditional distribution tables. Are there things we can infer about the distribution by just looking at the graph? This is interesting. Why is this interesting? Because now if somebody tells you, hey, I specified a distribution through a Bayes net, here's my graph. If by looking at that graph you can understand properties of the distribution they specified, that's nice, because that's much easier to do and often easier to eyeball things, have intuition about a graph, and have to go through this full joint table to build intuition about how your variables interact. So look at what can we infer by just looking at the graph. Then in the first lecture after spring break, we'll look at how we can answer numerical queries about these distributions without resorting to go back to the full joint, right? We know how to answer any query about the Bayes net distribution. You just built a full joint, we know how to work with a full joint, and then we can compute the answer. But then we have an intermediate step where we built a full joint. That's expensive. We'll see how to get around that, how to compute directly on these smaller representations to still be able to answer queries about the full joint distribution. All right, that's it for today.